Welcome to In-Silico Trials Real Impact, the In-Silico UK podcast that's revolutionizing the way we think about medical innovation. I'm Professor Alejandro Frangi from the University of Manchester, and I'll be your guide through this fascinating world of In-Silico technologies. In each episode, we'll dive into cutting-edge research and groundbreaking news that are shaping the future of medical product development and regulation. From computational modeling to simulated clinical trials, we are exploring how digital approaches are transforming healthcare, making it safer, more efficient, more equitable, and incredibly precise. So, whether you're a researcher, regulator, a member of the public, or a patient representative, or simply curious about the future of medicine, tune in as we unravel the complex world of in-silico methods and their real-world impact. Get ready to discover how computer-simulated trials are leading to very real breakthroughs in patient care. In-Silico Trials Real Impact, where algorithms and data are saving lives. Let's begin.
Welcome back, everybody, for another deep dive. This time, we're going to be looking at the world of digital twins.
Oh, cool.
Specifically, how they're being used in oncology.
Wow.
And the source material that we're going to be looking at is a 2022 scientific review article from Biophysics Reviews.
Okay.
And it's called Digital Twins in Oncology.
Makes sense.
So really diving deep into this pretty complex topic.
It is.
But it's a really fascinating idea, this whole concept of digital twins.
It really is.
So maybe back up for a second before we get too far.
Sure.
When you hear digital twin, what comes to mind?
Well, I immediately think of those virtual representations of cities,
Oh, yeah.
where they have the whole city laid out and you can zoom in on different areas and look at traffic patterns and all that stuff.
Yeah, exactly. And they use it for city planning and
exactly.
Resource allocation.
Yeah, and disaster preparedness.
Yeah.
What would happen if this area flooded or there was an earthquake? You can kind of simulate all these different scenarios.
Exactly. Or even airplanes. I think they have digital twins for airplanes now where they
It's really?
Yeah, where they can monitor the performance and predict when maintenance needs to happen. And
wow, that's amazing.
yeah, it's really fascinating. But how does that apply to something like cancer?
Well, it's the same basic principle, just applied to a much smaller and more complex system.
Okay.
So instead of a city or an airplane,
Right.
we're talking about creating a virtual copy of a tumor,
Okay.
a digital twin, if you will,
Huh?
that can be used to simulate different treatment scenarios and predict outcomes.
So basically you're taking a tumor
Yep,
and creating a digital replica.
exactly. And,
Right.
and just like those city or airplane digital twins,
Right.
this virtual tumor is constantly being updated with real-world data.
It's not just a static image, right?
Not at all.
It's like a dynamic living thing.
Exactly. It's a dynamic model that mirrors the behavior of the actual tumor.
Okay, so how do you even create that? How do you build that connection between the real tumor and this virtual one?
Well, the source article breaks down a digital twin into 6 core elements.
Okay.
On the physical side, we have the actual tumor itself with its current state.
So its size, shape, location, all that.
Exactly, all those physical characteristics.
Okay.
Then we have the observational data.
Which is?
That's all the information we gather from medical imaging like MRI and PET scans, but also biopsies, blood tests, anything that gives us insights into the tumor's behavior.
So you're pulling data from all these different sources.
Right. We need a comprehensive picture.
Correct.
And then we have the control inputs.
Control inputs.
These are the treatments we use.
Okay.
Chemotherapy, radiation therapy, surgery, immunotherapy, all those things.
Got it.
So those are the 3 elements on the physical side.
The real world side.
Exactly.
Okay, so what about the digital side?
So on the digital side, we're essentially creating a virtual representation of the tumor. And this is where those advanced mathematical models come in.
Mathematical models.
Yeah, we use these complex equations to essentially build a replica of the tumor in the computer.
Wow, so it's you're translating all that real world data into a language that the computer can understand.
Exactly. And once we have that digital representation, we can start tracking what the article calls quantities of interest.
Quantities of interest. Okay, give me an example.
Sure. It could be something like tumor growth rate
Okay,
or how the tumor is responding to a particular drug
got it.
or even how it's interacting with the surrounding tissues.
So you can see how the tumor is behaving in the virtual world.
Yep. And we can even manipulate those control inputs, those treatments.
Oh, so you can experiment with different therapies on the digital twin.
Exactly. And see how it responds.
Without actually doing anything to the real patient.
Exactly. That's the beauty of it.
That's amazing. But wait, you mentioned 6 elements.
Right.
What's the sixth one?
The sixth element is what the article calls rewards.
Rewards.
Think of it as the ultimate goal of the whole process.
Okay.
Essentially, it's the patient outcomes we're aiming for.
So things like survival rate, quality of life, that kind of thing.
Exactly.
Okay, so it's like you're creating this virtual laboratory
Right.
where you can test out different treatment strategies
Yeah.
and see how they might impact the patient's overall well-being.
Yeah, and without any risk to the actual patient.
That's incredible. It's like personalized medicine taken to a whole new level.
It really is.
But this whole digital twin thing,
Yeah.
that's not just for cancer, right?
Oh, no, not at all. It's being used in all sorts of industries.
Like what?
Well, did you know that car manufacturers are using digital twins for every car they sell?
Really? Every car.
Yeah, they're creating a digital twin for each vehicle that rolls off the assembly line.
Wow. What do they do with all that information?
Well, they use it for all sorts of things.
Like what?
Like monitoring the vehicle's performance,
Mm-hmm.
predicting when maintenance is needed.
Oh, wow.
They can even issue software updates remotely.
So they have like a virtual copy of your car
Yep.
that they're using to make sure everything is running smoothly.
Exactly. It's all thanks to that constant feedback loop between the physical car and its digital twin.
That's fascinating. But let's get back to the focus of our deep dive here. Cancer.
Sure.
Why are researchers so excited about the potential of digital twins in oncology?
Well, think about how we approach cancer treatment today.
Okay.
A lot of it relies on clinical trials, which are incredibly important,
Absolutely.
but they can be expensive, time-consuming,
Mhm.
and often limited in their scope.
And they also focus on the average patient in a group,
Right.
Not the individual.
Exactly. So even if a drug works for a certain percentage of people in a clinical trial,
Right.
there's no guarantee it will work for any one person in particular.
And that must be incredibly frustrating for patients and their families
It is, absolutely.
to be told, like, well, this drug has a 50% chance of working.
Right. It's like flipping a coin. And that's where digital twins offer a real breakthrough.
Okay, I'm intrigued. Tell me more.
Imagine being able to create a virtual model of your own tumor
Okay.
and then simulate how it would respond to different therapies.
So instead of relying on population averages from clinical trials, you're getting insights that are tailored to the individual.
Precisely.
It sounds like truly personalized medicine.
That's the goal.
So let's say I'm a patient facing a cancer diagnosis.
Okay.
How would a digital twin actually be created for me? Where does the process begin?
It all starts with data.
Okay, what kind of data?
Well, the primary source is medical imaging.
So those MRI and PT scans we talked about earlier.
Exactly. Those provide the crucial foundation for building the digital twin.
Okay, so those scans give you a snapshot of the tumor,
Yeah,
but the digital twin needs to be dynamic, right?
absolutely.
It needs to capture how the tumor is behaving over time.
You're exactly right.
So how do you do that?
That's where the magic of mathematical modeling comes in.
Okay, so you're taking those visual images from the scans
Uh-huh.
and then using equations to predict how the tumor will evolve.
Exactly. We use these models to simulate the growth of the tumor and its response to different treatments.
So if you give the virtual tumor a certain drug,
Yep.
you can see how it might react.
Precisely.
That's amazing.
Yeah.
But it sounds incredibly complex.
It is complex, but the potential benefits are enormous.
I can imagine. And I'm guessing this is where the power of AI and big data comes into play, right?
Absolutely. AI is a game changer in this field.
Yeah, because I can just imagine AI sifting through mountains of data, looking for patterns and insights that might be missed by the human eye.
Exactly.
Like, are there any specific ways AI is being used in this process?
Oh, definitely. For one, it can help analyze those massive data sets we were talking about, identifying subtle patterns that might not be obvious to us humans.
Okay.
It can also help accelerate those complex calculations that are needed to model tumor growth.
So AI isn't replacing doctors. It's more like augmenting their expertise.
Exactly. It's about giving them new tools to fight cancer.
It's like having a superpowered research assistant working around the clock.
I like that analogy.
It's pretty exciting stuff. I'm sure there are challenges too, right?
Oh, absolutely. This technology is still in its early stages.
So what are some of the hurdles that researchers are facing?
Well, for one, developing those mathematical models is a huge undertaking.
Yeah.
We need to make sure they accurately reflect the complexity of real-world tumors.
Right, because cancer is incredibly complex.
It is.
Every tumor is unique.
Exactly. And even with the perfect model, there's always going to be some level of uncertainty in our predictions.
Uncertainty is a big word in medicine,
It is.
especially when you're dealing with something as complex as cancer.
Yeah.
So how do you manage that uncertainty when you're using digital twins?
That's a great question.
Yeah.
And it leads us to a practical roadmap that the source article provides. They outline 5 key questions to ask when assessing the feasibility of using digital twins.
5 key questions.
Yes, it's like a checklist
Okay.
to make sure we're being thoughtful and responsible.
All right, I'm ready to tackle this checklist.
Great.
What's the first question we need to consider?
Well, the first and arguably the most important question is this.
Okay.
What are the goals for this digital twin?
So what are we hoping to achieve by using a digital twin in this specific case?
Exactly. We need to clearly define the purpose of the digital twin in the context of the patient's situation.
Okay.
What decisions do we want to inform? What outcomes are we aiming for?
Okay, I understand that in principle, but can you give me a concrete example?
Sure, let's go back to that high-grade glioma example.
Okay, the aggressive brain cancer.
Right, so let's say we're using a digital twin to personalize a radiation treatment plan for a patient with this type of tumor.
Okay.
What would our goals be in that scenario?
Well, I guess the main goal would be to kill the tumor.
Yes, but it's more nuanced than that.
Okay, how so?
We want to maximize tumor control while also minimizing damage to the surrounding healthy brain tissue.
Right, because you can't just blast the entire brain with radiation.
Exactly. It's about finding that sweet spot
Okay.
where we can deliver enough radiation to kill the tumor cells,
Mm-hmm.
but not so much that we cause serious side effects.
So it's a balancing act,
It is.
and the digital twin helps you find that balance.
Precisely. It allows us to simulate different radiation plans and see how they might impact both the tumor and the surrounding healthy tissue.
So it's like you're running virtual trials before you deliver any actual radiation.
Exactly. And that's just one example.
Wow, that's incredible. But we've only scratched the surface here.
We have.
I've got 4 more questions to go on our checklist
We do.
and a whole world of real-world applications to explore.
I can't wait.
So join us for part 2 of this deep dive, where we'll continue our exploration of digital twins in oncology.
See you there.
Don't miss it.
All right, so we've tackled that first question on our checklist for assessing the feasibility of using digital twins in specific situations.
Right, defining the goals.
Exactly. And in the case of using a digital twin for radiation therapy for a high-grade glioma, that goal is to determine that optimal radiation dose and schedule for that individual patient.
Right, to maximize tumor control while minimizing damage to the surrounding healthy tissue.
Precisely.
Okay, so what's the next question on our checklist?
So the second question is this. What level of complexity is needed in the digital twin?
Okay, so how much detail do you actually need to include in the model?
Exactly. And that really depends on the goals that we define in the first question.
Okay, so in the case of adaptive radiotherapy for high-grade glioma, what level of detail would we need?
So for something like that, we would need a model that can capture the spatial distribution of the tumor cells, their sensitivity to radiation, the location and vulnerability of the surrounding healthy tissue.
Okay, so it's not just about modeling the tumor itself.
Right. It's about modeling the entire environment.
Right, because you need to understand how the radiation is going to affect everything in its path, not just the tumor.
Exactly.
So that sounds like a pretty complex model.
It can be, yes. And the more complex the model,
Yeah.
the more data you need to feed into it.
And the more computational power you need to run it.
Exactly.
So there's trade-off there, right?
Absolutely.
Between complexity and feasibility.
You got it.
Okay, so we've defined our goals. We've figured out the level of complexity we know. What's next?
The third question that we need to ask ourselves is this. Does a proper mechanism-based mathematical model exist?
Okay, so this is about the equations that you're using to actually describe what's happening in that virtual tumor.
Exactly. And this is a really crucial point because the mathematical model is the engine that drives the digital twin.
It's like the brains of the operation.
Yes, exactly.
Okay, so in the case of high-grade gliomas and radiation therapy, do we have the mathematical tools we need?
Fortunately, in this case, the answer is yes.
Okay, good.
Scientists have been developing mathematical models of tumor growth and response to radiation for decades.
So we've got a pretty good understanding of how those tumor cells are going to react to the radiation.
Yeah, and those models are constantly being refined and improved as we learn more about the underlying biology.
That's great. But even with the right model, you still need data.
Oh, absolutely. That brings us to the fourth question.
Okay, hit me with it.
Are the required data available and accessible?
Right. You could have the most sophisticated model in the world.
You got it.
But if you don't have the data to feed into it, it's not going to do you much good.
Exactly. And when we're talking about digital twins in oncology,
Yeah.
the primary source of data is medical imaging.
So those MRI and PT scans we keep talking about.
The same.
Okay, so you need those scans to build the initial model of the tumor.
Yeah, but you don't just need one scan.
You need multiple scans over time, right?
Exactly. We need what's called longitudinal data.
Okay, to see how the tumor is changing and responding to treatment.
Precisely. That allows us to continuously update the model and make sure it's accurately reflecting what's happening in the real world.
That makes sense. But I imagine getting all that data can be a real challenge.
It can be, yes.
You've got different hospitals using different imaging equipment, different patients being scanned at different frequencies.
Right. It's a logistical nightmare sometimes.
It's like trying to herd cats.
Yeah, it can feel like that sometimes, but we're working on it.
Okay.
There are a lot of efforts underway to standardize imaging protocols and improve data sharing between institutions.
So hopefully it'll get easier in the future to access all this data.
That's the hope.
Okay, so we've talked about the goals, the complexity of the model, the mathematical equations, the data. What's the fifth and final question on our checklist?
This one might seem a little bit philosophical, but it's really important. Can the uncertainty be characterized?
Uncertainty. But I thought the whole point of using data and models was to reduce uncertainty.
It is, but in reality, there's always going to be some level of uncertainty.
Especially when you're dealing with something as complex as cancer.
Exactly, and we need to be honest about that uncertainty.
So even with the best data and the most sophisticated model, you can't say for sure what's going to happen.
Right, we can't predict the future with 100% certainty.
But we can get a better sense of the possibilities.
Exactly, and we can quantify that uncertainty.
Okay, so instead of saying this treatment will definitely work, you could say there's an 80% chance that this treatment will work.
Exactly. It's about giving patients realistic expectations.
And being transparent about the limitations of the technology.
Exactly.
So these 5 questions are really helpful for thinking through the practicalities of using digital twins in oncology.
They are. They provide a framework for making sure we're using this technology responsibly and ethically.
It's great to see that researchers are approaching this with such care and consideration.
They are. It's an exciting field, but it's important to proceed with caution. And speaking of exciting developments, in the next part of our deep dive, we're going to explore some of the real-world applications of digital twins in oncology.
I can't wait to hear more about that.
Yeah.
So we've explored those 5 key questions for evaluating whether or not digital twins are ready for prime time in specific clinical situations.
Yeah.
And I'm really eager to see how this is all playing out in the real world.
Me too.
Where are we seeing digital twins actually making a difference in patient care?
So we're seeing a lot of exciting progress in treatment planning, especially when it comes to radiation therapy.
Oh, yeah.
This is where we're really seeing digital twins shine, you know?
Okay, I'm ready for some real-world examples. Lay them on me.
Okay, so picture this. You're a doctor, and you're treating a patient with a really complex tumor.
Okay.
Like in a really sensitive area of the brain, like near the brainstem or the optic nerve.
Oh, wow. Yeah, those are delicate areas.
Exactly. And you need to deliver radiation with incredible precision.
Yeah.
Making sure you hit the tumor effectively while avoiding those vital structures.
Yeah, those are high stakes.
Oh, absolutely.
One wrong move could have devastating consequences for the patient.
Yeah, you really don't have much room for error in those situations.
Right.
And that's where digital twins come in.
Okay, how so?
Well, they allow doctors to essentially simulate different radiation plans on the virtual tumor.
Oh, so it's like a practice run.
Exactly. You can experiment with different beam angles, intensities, and schedules all within the digital world before you deliver any actual radiation to the patient.
That's amazing. So they can fine-tune their approach, make sure they're minimizing the risk to healthy tissue.
Exactly. And that's not all. Digital twins can also help predict how well a patient might respond to a particular drug.
Okay, hold on. So you're saying that instead of just using general statistics from clinical trials, you can actually get insights that are tailored to that specific patient.
That's right.
That's incredible. How does that even work?
So we can integrate all sorts of patient-specific data into the digital twin.
Okay, like what kind of data?
Their genetic information, tumor characteristics, even their medical history.
So you're creating this really comprehensive virtual profile of the patient.
Exactly.
Yeah.
And then we can run simulations to see how that virtual patient might react to different therapies.
So it's like a virtual clinical trial, but for just one person.
That's a great way to put it.
That's incredible. This technology really does sound like it has the potential to revolutionize cancer care.
It does, and it's already starting to make a difference in the lives of patients today.
That's really inspiring.
It is, and we're just scratching the surface.
I'm curious, what does the future hold for digital twins in oncology? Where do we go from here?
Well, one area that's really exciting is incorporating real-time data into these digital twins.
Okay, real-time data, what does that mean?
So imagine wearable sensors that track vital signs, blood markers, even tumor activity.
Wow.
All feeding information back into the model.
So you're constantly updating the digital twin, making it even more accurate.
Exactly. And as artificial intelligence and machine learning continue to advance, we can expect even more sophisticated models capable of analyzing massive data sets and uncovering patterns we might never see on our own.
Yeah, it does feel like we're on the cusp of a revolution in cancer care.
I agree. Digital twins have the potential to transform how we diagnose, treat, and manage cancer.
It's a really exciting time to be in this field.
It is, absolutely.
But it's important to remember that this isn't a solo effort.
Right.
It's going to take a village.
Absolutely. It requires collaboration between biologists, clinicians, mathematicians, computer scientists, and many others, all working together to create a future where cancer is no longer a death sentence, but a manageable condition.
Wow. That's a powerful vision. A lot of brilliant minds coming together to tackle this global challenge.
That's right.
So as we wrap up our deep dive into digital twins in oncology, what's the one key takeaway you want our listeners to remember?
I'd say the most important takeaway is that digital twins are not just some futuristic concept. They are a tangible tool that's already making a difference in the lives of cancer patients today. And as the technology continues to evolve, we can expect even greater breakthroughs in the years to come.
It's a message of hope and progress, and a reminder that we're living in an era of incredible scientific advancement. Thank you for sharing your expertise with us today. It's been a fascinating conversation.
My pleasure.
And to our listeners, thank you for joining us on this deep dive into the world of digital twins in oncology. Keep those minds open, keep asking questions, and stay tuned for more fascinating deep dives into the world of science and technology.